Hello, friend. My name is Derek Harder, and in this video, we're going to continue our discussion of convolutional neural networks and deep learning. So, in particular, in this video, what we're going to do is look at a complete end-to-end example of creating and training a small convolutional neural network on a relatively small data set. All right. So let's go ahead and get started here. Okay, so in this video, we're going to look at training a convolutional neural network from scratch using the Keras API, and then once we build it, we're going to build one that will be overfitting. Then we're going to look at a couple of things to fight that overfitting. Using data augmentation, a few other things in this video. So we're going to use the cat and dog data set. You might be a little bit familiar with this. We're going to be getting it directly from Kaggle, and it has like 25,000 images or something in the training set alone, plus another set for testing. We're going to extract a smaller subset, so we'll use 2,000 images for training, 1,000 for validation, and 2,000 for testing here. Okay, split evenly between dog and cat pictures. So this is an image classification task that we're going to be doing, and it's balanced. So we have exactly equal numbers of dog and cats images. So all we want to do is build a image classifier that if we give it an image, we'll say it's a dog or a cat. Right? Our first model here, we're going to get it so that it will be overfitting. So then we'll later on look at a new regularization technique that we haven't talked about, data augmentation, in order to fight that overfitting. So just a few words about this data here. We're using the Kaggle data set that our textbook used. So you will have to download this. This is too big for me to put into our class repository. So if you click on this link, and you will have to create an account, but if you click on that link, you should be able to download all. You'll get a zip file that will have inside of, once you unzip the file, you'll actually have two zips inside of it, a test and train, and you'll want to unzip the zip file. So that file you download actually has 25,000 images, and I set it up so for this code to work underneath here. It's expecting that I put it in our data subdirectory for the project, in a subdirectory called dogs versus cats. Okay, so if I look at my repository here, this is my NNDL repository. I created a subdirectory called dogs versus cats, and then I unzipped that test zip file and that train zip file. So if you look in the train, we're actually not going to be using the test, so you don't really have to unzip that. We're just going to be sampling 5,000 images out of this 25,000. So these are just all images. There's 12,500 cats, and 12,500 dogs. So 25,000 images of cats and dogs. They're all of different sizes. They're not too big, but they're all slightly different sizes. Okay, so we're not going to use that full 5,000. We're going to build a image classifier that we're not going to use the full 25,000. So we're going to build an image classifier on a randomly selected subsample of that. Actually, it's not random. We're just going to pick the first 5,000 dogs and cats out of this here. But we're going to set it up in a particular directory structure. We do this for a reason. So we'll talk a little bit about the Tensorflow Dataset object that can flow out pictures like this. So we have to structure it so that inside of the directory we want to flow stuff out of, we have three subdirectories: train, validation, and test. So I'm going to bring back up my file browser. We'll notice for some reason, so Kaggle will call it dogs versus cats. So this might show some bias on our author's point of view here, but he renamed it cats versus dog small here. So we need to end up with a subdirectory called cats versus dog that has a test, train, and validation subdirectory. Inside of those each have two further subdirectories that have the things for one of the classes of our binary classes, and in there it's going to be all of the 2,500 images that we will use as our test set for the cats, and then we'd have images we use the test set for the dog. Likewise in the train. So all these have a cat and a dog subdirectory. Okay. So that's all this cell does here. I've already done it. There is a guard here. So basically it assumes that if you don't have a subdirectory called data cats versus dogs, it'll do the work. But if you do have that subdirectory, it'll call this to create it for you from the raw data of 25,000 images. Okay. So you'll need to run that to select our sample. So, you know, if you need to put these in some different location, just change these paths to point to where the data is that you unzipped, and then the location where you're going to put it, right? So all this notebook, though, is going to assume, so when we create our TensorFlow dataset object, it's going to assume that this path here, new base directory, has that structure, so it can flow in the images. Okay? So real quickly, just a few random, so three random cats from the what was it, the training set, and 3 random dogs from the training set. So notice that these are all of different sizes, so we're going to have to do something about that. So a neural network input can't take things of different sizes, so we're going to have to resize them so they're all a common size before we can actually do any training or testing with images that come in. So we're going to use pretty much the same structure that we had in our first example of a convolutional neural network. So this one is again going to be a stack of alternated convolutional 2D layers and max pooling layers. Okay, so we're going to use pixel sizes 180 by 180. So we're going to have to resize all of our images to this size, and they are color images. So there's going to be 3 RGB channels that come into our first convolutional layer. And you'll see that we're going to be downsampling, so we'll end up, for the final result, that we have feature maps of size 7 by 7. Yeah. And you'll see here, well, let's go ahead and show the model. So the convolution layers progressively take the filters again, although we have a few more layers than we had in our first example, so we go from 32 up to final 256. Convolutional layers, each one with a max pooling layer. All the max pooling layers are doing 2 times downsampling. Okay. But otherwise, this is similar to what we've seen before with our 180 by 180 size pixel with 3 color channels coming as input to the top of this hierarchy. Right? And then we are doing a binary classification, so we flatten this out to a dense layer this time. That just uses regular sigmoid activation to get a 0 or 1 output. Okay, and then we'll use the binary cross entropy as our loss function for our network here. So yeah, so I created a model. So again, we're using the Keras functional API to create the model here. Let's go ahead and look at the summary of our model, just to confirm the property. So you should know from the previous video why. When we, I did skip over this rescaling layer. So this is a simple layer. It doesn't have any parameters that are learned in it. This does the normalization. So for each color channel, we have a value from 1 to 255. So instead of converting that to an integer from 0 to 1, we just add in a rescale layer here. So we don't have to assume that any image we input has already had that conversion to a floating point value here. So you see that rescaling layer first with no trainable parameters. So you go, again, as usual, each of the convolution layers, it ends up chopping off 2 from the length and width. And it creates the number of filters or feature maps as the output. So we progressively go then, because of the downsampling, from the 180 by 180 input to our final 2 convolutional layers that we do, end up taking it down to a 7 by 7, which is with 256 filters or feature maps, which gets fed into the final dense classifier that we have in the network. So this is the network we're going to use to train with. So this pattern should be familiar to you now, right? And you'll see this pattern repeated over and over. So we've got, 5 different convolutional layers that progressively have our feature maps smaller and smaller, but that means that they're actually covering larger and larger areas of the input. And then the number of filter increases as we go from the input to the output of this network. So conceptually, this should be learning more and more high-level features as it goes through the network here. All right. So with that, we're ready to go ahead and compile and see how it works. No, we got to talk a little bit about some pre-processing, but we'll compile. I already mentioned we are doing a binary classification, so we should use the binary cross entropy. And since accuracy makes sense here, we'll go ahead and monitor the accuracy metric doing our train. So we already created the data structure that we need. So this is a first look at using this TensorFlow Dataset object. So this is kind of nice and convenient, so we might come across this again. So if you structure your directories like we showed, so we've got split up into train, test, and validation subdirectories, and inside of those directories are further subdirectories, one for each class, right? So since it's binary classification, there's only 2 subdirectories with cat and dog images. So this is needed for once you get to bigger problems like this, because you can't necessarily hold all the data in memory you're going to be used to train with. Okay, so this data would probably fit in memory. We've only got like 5,000 images in our training and validation data sets here. But you could have, if you're using like the full ImageNet data set, there would be way more than you could actually fit in your computer memory. So that's kind of what the purpose of this dataset object is to flow stuff in so it can be fed in for training and validation. Right? So there is a method that will create one of these data sets for you, and we're basically just pointing it at the train, validation, and test subdirectory that has our new sampled small sample data set of the cats and dogs here. So just a little bit more about this dataset object. So you can kind of think of it as an iterator. So once you create this, so for example, here we'll create another TensorFlow dataset, but we'll create it where we're inputting a array of random numbers. Okay, so you can think of this as just an array of 1,000 samples that have 16 features here. So you can just do like a for loop over the data set. The enumerate here will also give us the index of each item. Okay. So this one, we stop the loop after 1 iteration, so that just gets the, after 3 iterations. So notice the first 3 things that pulled out were just 3 individual samples. So sample 1 at index 0 had 16 features, and then the sample at index 1 and the sample at index 2. But you can also batch these, so this is how it would normally be fed into the fit method when we pass this to a Keras model to fit a model. So if you say the batch size is 32 and iterate over it, it'll pull out samples of 32 of each one of these randoms that have generated data here. Okay? There's a broad range of things that I want of other dataset methods you could use to like shuffle, prefetch, and things. So generally, it's relatively useful. So yeah, a quick example of the map. So if we needed to reshape those into 4x4 inputs for our samples, we can map that data in and then flow it out of the data set like that. So specifically for the training data that we're using, so we've got this in one of those TensorFlow data sets called train dataset. So for example, there's other stuff you can do. It's not a simple iterator, but like these were the class names that it figured out because there was 2 subdirectories in the train subdirectory. So default, I might skipped over it, but if we iterate over the trained data set, it was already a batch data set. So if we look at what it pulls out, it'll pull out a batch of datas and labels that we would use for training here. So in this case, the first batch was shaped 32 samples that were 180 by 180 pixel images. And they're colored images with 3 channels, and our labels, we have the 32 labels, one for each of the samples that we pulled out we're going to use for training here. And notice these are already all resized to 180 by 180. I forgot to show a little more details on here, right? So this is when we created the TensorFlow dataset, we not only specified the directory, but we set it up to do a batching flow. So we pre-specified the batch size, and one thing that this thing do, it's set up to actually flow images. That was one of its primary purposes. So you can ask it to resize. So whatever the variable sizes of the images are, it will put it through a resizing process that makes sense. So that you end up with 180 by. So with our TensorFlow dataset object set up, so as we saw, we'd already pulled down the first batch, size 32. So for example, we can look at the sample, the first sample at index 0. Notice we don't have to reshape, but that happened to be the sample 0 that was coming in as the first image input that we would have done with training. So with that, let's go ahead and fit our model and see how it does. Okay, so we're gonna be using checkpointing like we've seen before in order to keep track of the model that obtains the best validation loss while it's running. So that'll be the one that's in our checkpoint file here. Let's try it for 30 epochs and see how it fits. Okay. So this shouldn't take too long, even on CPU, because the data set is relatively small. But let me go ahead and pause till we're done with our first fit here. Okay, so let's see the results of training this first model here. So, we could look through here and see, like, for the training accuracy, keeps getting, the training loss keeps getting lower and lower. It's being pushed down towards 0. And look at the training accuracy. It's going up, approaching 99%, reaching 100%. But the validation actually doesn't look so good. But, as usual, let's plot the learning curves to get a visualization so we get a better idea. So you should recognize this pattern. This looks like a classic overfitting, right? Our model's too powerful. So at some point, validation loss stopped improving, and it just started exploding, going back up again, right? And at that point, so this you should usually see around sometime before epoch 10. So after epoch 8 or 9, the validation loss stops improving, and the accuracy stops somewhere around 70%. Okay. So let's look at a final. So we saved the best model, the one that obtained the best validation loss, which is probably this one here at epoch 7 or 8 or so. So let's load that back in and see what we actually get on the training data. So, usually you get something around 70%. The highest, I have seen something maybe a little bit above, close to 74%, but that's what you'll get. All right. But because this is overfitting, we should expect that we can do much better on accuracy on data we haven't seen before. Okay, so overfitting is causing us. It's causing us a problem here. So it's always caused by having too few samples to learn from. So the density of the representation of the manifold is not dense enough. So we get the kind of the classic overfitting. So we've seen several techniques for fighting overfitting in neural networks, including doing weight decay or applying dropout layers, which are specific to neural networks. So this is another method that we'll introduce to add to your toolbox for fighting overfitting, known as data augmentation. So data augmentation works particularly well for when you're doing image classification. So when your input data are images or videos. So the idea for data augmentation is we need to perturb the inputs randomly a little bit, so that they're not exactly the same input as before. So using data augmentation, we can actually set it up so that during training, the model never sees the exact same input ever, more than once, right? So that can greatly fight overfitting, right? And the reason why this is particularly good for image data is it's easy to make small random transformations that are still plausibly images that you would see as input. So that means technically we would say that they're still probably on the input manifold that we want our model to learn. Okay, so in this example, we'll just apply three kinds of random perturbations for our images, right? So Keras provides these layers. These don't have any trainable parameters. We will insert this set of three layers in between the input and the first actual layer that has trainable parameters for our network. So there's others than these, but for example, this one, 50% of the time, it'll randomly flip only on the horizontal axis. So we won't flip it upside down. We will just flip it vertically, so it'll be mirrored. We'll do some random rotation. So this means that we will pick a random rotation between negative and positive 10%. Right? So it could pick it at 0, but usually all the images will be rotated a little bit, as if the person holding the camera was tilted a little bit this way or that. Likewise, we can simulate being a little bit closer or further away, so we might zoom in or out by 20%. Right? So those are augmentations that we'll use here. So for example, if we take the first image from our training data set, from our TensorFlow dataset item, take out one item. So here's the result of doing that random perturbation 9 times here. So usually you'll see about half the images flipped, but it is random, right? So 7 of the 9 still have this orientation. 2 of the 9 were randomly flipped. And if you look closely, you'll see some are a little bit closer and further away. So here we can see obviously some rotation from the others. So there was quite a bit of probably like close to the positive 20% that we can get. Right? So that's happening. That's what's happening with those 3 data augmentation layers. They're just randomly doing those transformations on the images. So with that, so experience also shows us that these images are still highly correlated. So they will do really well in helping to fight overfitting, but they won't completely keep it from happening. Okay? So overfitting can still happen even with this kind of random perturbations doing this data augmentation. So, experience has shown that we should add a dropout layer as well. So you should be familiar with these. So we're adding some dropout with 50% dropout to also to fight overfitting in our modeling. So with that, notice all we have to do is plug in those 3 layers using that sequential set of 3 layers here. And we just plug in a dropout after the final convolution before we make our final decision of whether it's a cat or a dog. All right. So let's go ahead and compile and run our model again with augmentation and see what happens. So it will take longer, since we're fighting overfitting, it'll take quite a bit longer before it gets into a good range, so we'll train for 100 epochs this time. So let's let that run. Okay, so we're done fitting our model here, and so instead of trying to look through the output while fit was running, let's go ahead and visualize our learning curves like we usually do. So you should usually see a result like this, although often validation loss will stay more steady once it stops improving. So this still looks like it might be a little bit overfitting for this particular run that I had. Okay, so our lowest validation loss probably occurs somewhere here between epoch 40 and 60. But remember, we were only achieving about 70% accuracy for the model that was overfitting before. So we fought that a lot. So again, we might be overfitting. If we keep going, it looks like training loss is still continuing to go down and accuracy maybe going up a bit. But we've probably reached about the peak of validation loss we're going to get with these settings here. Okay. So let's go ahead and reload the model that was obtain the best loss and see what we get for a final check on the the test data with that best model. So, you know, this is typically, you'll get around 80%, right? So we improved from somewhere around 70 to 80% by using data augmentation and a dropout layer here, okay? So further tuning of this model, you know, so this indicates we're still maybe overfitting. So we might be able to actually get that up a bit, 80, 85%, okay? But in our next video here, we're going to actually look at using pre-trained models. So we'll actually be able to improve this quite a bit, a lot more than this using pre-trained models. Okay. So, just a few summary of some of the important things that we brought up in this video. So always remember that the basic architecture of a convolutional network is typically a sequence of convolution layers followed by max pooling layers, okay? So in this example, we had one convolution layer followed by a max pooling layer. We had 3 different levels like that. So, and also typically the feature map sizes will go up. So the number of features that's learned by each convolution will go up. So we'll start with a small number, which represents like edge detections, vertical and horizontal lines. Usually that's what will be learned at the lowest level of the hierarchy. And then as we go up, we'll have more and more of the features for each subsequent convolution layer. And they'll learn larger and larger conceptual items in the visual hierarchy. Okay? But also, because of the max pooling downsampling that we usually use for convolutional networks, that means that the width and height of those feature maps will steadily decrease. There's 2 reasons of that. So, you know, if we don't downsample, we end up with patterns down at our highest level of the hierarchy that are still focused on a relatively small patch of the original input image, which we don't want. So at the end, we want relatively larger, you know, we want the features that were recognized on the image to be in relatively larger patches of the original image. So like in the upper left quadrant or upper right quadrant or something like that. Maybe only breaking it up into 4 or 9 kind of pieces where we might recognize there's a face here, there's a cat here, there's a tree there, that kind of stuff. Okay? But also, you know, it's an argument about overfitting. So if you don't do that downsampling, you'll end up with a huge number of parameters that go into your final dense layer that make the final determination of like your classification, which will make overfitting worse. Okay? So also remember, we looked at Tensorflow Dataset objects, which can be useful to set up a dataset workflow. So especially if you've got too much data that more than can fit into memory, you might want a dataset object to flow it in while you're training and validating. Also, data augmentation can be a very helpful technique. It can be used for other kinds of data sets than image data sets, but it's particularly useful and easy for image data sets to use data augmentation. Okay. So that's it for this video. I hope that was useful for you for understanding how a convolutional neural network is created and trained from scratch. So stay tuned for the next one, though, where we will look at using pre-trained models where you can really get a big boost in performance if you only have kind of a small data set to work with. By 180 size pixel images that come in as input.